where you're given the two initial conditions. So why don't you try it first, and then I'll do it. Problems you have on this first exam are really quite simple. All along. And then there's problems on Laplace transforms they're going to be due on the 21st. And our last day of class is the 19th. So let's see. Okay, so you should be working on this problem. You should be trying to solve this problem using the method of Laplace transforms, okay? And you will have a problem like this, a second order differential equation that you have to solve by method of Laplace transforms. Now you can also solve this problem by the method of undeterminate coefficients, but you have to solve it by Laplace transforms. I want to see that you're able to solve basic differential equations using Laplace transforms. Okay, so there's 17. It's amazing that people don't come. The people that don't show up are the ones that are not doing as well. So 17, 5 people missing. Okay, I'm going to give you, my plan is not to keep you to full time today, seeing that you have an exam to do and you can use the extra time, but we'll see. There's something I need to make sure that I cover that you need for the exam. And now will be the time too, if you have trouble with this problem, to bring up any questions.
Professor?
Yes.
I was actually wondering if you could go over the minute details behind identifying a regular single point and an ordinary point, because I still don't understand the difference.
Okay. We can go over that again. Okay, I'm going to give you to 10 after. May take a little bit longer, but yeah, I'll give you till 10 after. All right, let me go ahead and solve this problem. Let's see something here now. So first thing, I sometimes forget whether the dot is here or here, but I could derive it if I forget. You know, I know how to come up with this formula. So first of all, this is the relationship we found yesterday to find the second derivative, right? This little Laplace transform of the second derivative is given by this, where this is the initial condition of the function and then the first derivative, right? So that's the problem we're trying to solve. So so this here now, this is going to become s squared, right? Well, first of all, I take the Laplace transform of both sides, right? Let me do this. Right? I take the Laplace transform on both sides. When I take, and I could break this up into two parts, right? Because it's a linear, Laplace transform is a linear function. So this here becomes s squared, big S, right? And then it's going to be minus s, but this is 1, right? This is, we're told that this is 1. So this is just times 1, and then minus minus 1, right? There's no s in front of here, all right? And then this here is just going to be minus 4, right? And then this is going to be, right? When I take the Laplace transform of x, you know, we just write that as big X of s, right? I should make this a lowercase s, lowercase x. Okay, everybody's with me so far? All right, and then this is equal to 0. All right, that's equal to 0. So I could bring this over to the other side. I want to solve this for big X of s, right? X in the s domain. So let's see, I can write this as minus 4. Then this is, right? I just bring over the s and the 1 over to here, right? And so now I can write this as I could factor out the big X and right. Okay, so now when I solve this, s squared minus 4, right? Okay, now what do I do? Well, I got this s squared minus 4. What I'm going to do is I'm going to break this up. I'm going to write this as a. Well, I'm skipping a step. I don't want to skip a step. I'm going to write this as s plus 1, and this is factorable. So I'm going to factor this into s minus 2 and s plus 2. When you see an s squared factor, okay, if it's of this form, okay, so now I'm going to break this up into partial fractions. I'm going to write this as a over s minus 2 and plus b over s plus 2. Okay, so far so good. Okay, so now I'm getting, you know, when I multiply the entire equation by s minus 2, s plus 2, this is going to become s plus 1 is equal to a times s plus 2 plus b times s minus 2. Okay. All right. So now if I let's see, the easiest way to do this is to let's see, if I let S equals -2, then this is 0, right? This is 0. And this is going to be, so this is going to be 3 over, this is going to be 1 over here, right? If I let this is going to be -1, this is going to be -1. And this here is going to be -4. So I'm getting that B is equal to 1 over 4, right? So B is equal to 1 over 4. Now, what about A? Well, I think I can fit it here. If I let S equal to 2, right, then this becomes 0, right? This becomes 0. And then this is going to be 3. I'm going to have 3 is equal to 4A, right? So, so this is telling me that, that A is equal to 3 over 4. Okay, so now I got, all right, so what do I have now? So, do it like this here. What do I have here? So now I got that this is A here, so that's 3 over 4. 3 over 4 times 1 S minus 2, right? Plus B was equal to 1 over 4, right? 1 over 4. E, oh, I'm putting down the answer. 1 over 4 S plus 2, right? Yeah. B had the plus 2. A had the excuse me, B had the the plus 2 here. Okay. All right. So now I solved it. So now I can take the inverse Laplace transform, right? When I take the inverse Laplace transform, I could take this 4 out of 3 out. Okay. And so what is this? Well, this is just x to t, right? And this is 3 over 4. Now, what is this here? When I did the inverse Laplace transform of this is e to the at to the 2t, right? That's one of our Laplace transforms. And then this here is 1 over 4, and this is e to the minus 2t. So that's the solution. That's our answer. Let me see if it's, make sure I didn't make a mistake. Yeah, that's it. That's the answer. Okay. So that's the solution to this initial value problem where we had x double dot minus 4x. I think the one I gave you a second is actually easier than this one. So if you do this one, you should have no problem with the one that's on the exam with these initial conditions. I made it a little bit easier that I think one of these is 0. And that actually simplifies some of the algebra. Yeah, so you do have a second order differential equation where one of the initial conditions is 0, and that simplifies the algebra. But notice that we could check this, right? It's probably not a bad idea. Let me quickly check it. Well, first of all, if I put 0 in here and 0 in here, I do get 1, right? So the initial condition satisfied. And if I take the derivative of this, let's see what happens. This is going to be this will be plus 6 over 4, and then this is going to be let's see, this is going to be minus 2 over 4, right? When I take the derivative of this, right? So now when I put 0 in here, what do I better get 1. So when I put 0 in here, this is supposed to be equal to 1. So this is yeah, so this is 1 and this is 1. So I'm getting 4 over 4, which is 1. Okay. So the initial conditions check out. And if we take, well, also, so, okay, so the initial conditions checked out. And if you remember, let me do it over here. You know, the method that we already learned, if I have this differential equation here, if I want to find the general solution to this differential equation, right, this would just be m squared plus 4 is equal to 0. So this is m is equal to m squared is equal to 4. So m then is going to be equal to plus or minus 2, right? So the general solution to this differential equation is indeed C1 e, I guess just let me put what I, C1 e to the 2t plus C2 e to the minus 2t. So this is the general solution of this differential equation that we learned how to solve. All right. So once again, the purpose of these problems is that you, I want you to understand, you know, a problem like this, you probably wouldn't solve by Laplace transforms. You probably would solve it using the method that we already learned. But I want to make sure that you learn how to solve some of these basic problems. The real advantage of Laplace transforms is when you have a non-homogeneous differential equation and you have a piecewise function. All right. And so it turns out that, or you have a spike, you know, maybe you have a certain voltage in an electric circuit and suddenly there's a big spike. Well, you can't solve that by the methods that we already learned, but we're going to learn how to solve that using Laplace transforms. And that'll be on the next exam. Okay. So this first exam, this first part of the exam of the Laplace transforms is basic. Okay. So, all right. So what I want to do now, though, there is another property you need for the exam. So let me go over that that problem. Well, first of all, are there any questions on this problem? Okay, so everyone's going to get a problem like this right on the exam. All right. Now there is another for the exam. You do need another. Let's see. Okay. I'm going to tell you what chart I'm on. Okay. If you go to my Laplace transforms on Blackboard, I'm looking at chart 12. Okay, chart 12. All right. Now, this is a property that you can also need on the exam. And that's the, I'm going to actually derive the property, but it's the fact that if you have the Laplace transform of e to the at, right, and then you have some function, that's going to be equal to the whatever the value of this function is, but then it's shifted. It's shifted by a, where a is whatever you have up here. Okay. Now, there's a very simple proof of this, and I'm going to solve some problems. When I solve the problems, it should be straightforward. Let's see. I lost. Okay. So let's see here now. So like I said, I'm on chart 12 of my Laplace transforms on Blackboard. Okay. So let's see. So remember now, the definition of the Laplace transform. Have some function of t. It's equal. We call this big f of s, right? And that's equal to the integral from 0 to infinity of e to the minus st. I'm going to show you that this is true. And if I let s become s minus a, right? Then what's going to happen here? That's all I'm doing is letting s become s minus a. Then this becomes s minus a, the integral. I don't think your book has this derivation. And then this is e once again. So now this has become minus s minus a, right? T dt, f of t dt. So it's all I did is I said, let S go to S minus A. So I get this now. All right. But what is this? But now I can write this like this, right? I think I can make it clearer than what's in my notes, actually. Yeah, I can write this now as the integral, right? Of yeah, let me write it like this. S T and then times AT, right? I'm just rewriting this. I got the minus S here, this minus cancels with this minus. And I can write it like this. But what is this? Well, this here now would just be the Laplace transform of e to the AT, right? In other words, the function is now just replacing this. Okay, so it's just the Laplace transform of that. I should put Laplace transform here. If you understand the proof, that's fine. But what's more important is how to use it. Okay, so that means the Laplace transform of e to the AT, right? Because this is now my new function, right? This is the new function, so that's that. All right, so this is the key thing then. So the key thing we need to understand is that, and now we'll do some problems. That this is the Laplace transform of e the AT. Well, the Laplace transform of this is equal to that, okay? And then there's also the inverse, right? The inverse Laplace transform. Inverse Laplace transform is just given by this. Okay, all right. Questions? All right, so now let's, is there a question? I'm gonna solve some problems now to show you what I mean. Okay, how do we use this property? And this property is gonna come up in one of the problems that that you have on the exam. Okay. All right, so let's see now. Okay. So remember now, the just to remind you, the Laplace transform of the cosine of 4t, that's equal to s times s squared plus 16. Okay. Right, that's the Laplace transform of the cosine. But now, suppose I told you that I wanted the Laplace transform of e to the minus 2t times the cosine of 4t. Well, remember now, let me write here's our property, right? The property is that I got the Laplace transform of e to the AT times f to t is equal to f of s minus a, right? That's the property that we just derived. Okay, so I know this is true, right? I know that the cosine of 4t is given by this, all right? So now if I want to find the Laplace transform of e to the minus 2t times the cosine of 4t, well, if I compare this with this, right, this is just going to become s. Well, the s is going to be, this is going to become s plus 2, right, over s plus 2 squared plus 16. I hope you see that, because here I got, remember now, this is a plus a here, right? There's a plus a here. So, and there's a minus a here. So, so you see, we're shifting this s to be an s. If a is positive, right, we shift this s to be s minus a, right? So here I got a plus 2, here I got a minus 2. So I have to shift this s. I'm shifting the s here to be plus 2. All right. So this is the Laplace transform of e to the minus 2t times the cosine of 4t. right? Let me do another problem. Let's say we have t cubed. Okay, we know that t cubed is equal to this, right? Let me, let's see. Let's see, remember now the Laplace transform of t to the n is equal to n factorial divided by s to the n plus 1, right? This is the Laplace transform of t to the n, right? So if I'm just dealing with the Laplace transform of t cubed, right? That's going to be, it's cubed here, so there's going to be 6 factorial. Excuse me, it's going to be 3 factorial, which is 6, right? That's how I get the 6. And then, and this is t cubed, so it's n plus 1 here, so this is s to the 4th, all right? But now, suppose I want the Laplace transform of what I have in my notes here, of e to the 5t, I guess I have a plus. What is this equal to now? Okay, well, once again, I have to shift this s 5 units, right? So in other words, the Laplace transform using this property, right? And using this, the Laplace transform of this is 6 s minus 5 to the 4th, right? This is going to be 6. It's going to be s minus 5 because I have to shift this. I have to shift this s. This is sometimes called the translation of the x-axis theorem. I think that's what your book called it. Or it's also sometimes called the first transaction theorem. We can also take a look at the second and other ones. Okay, so any questions on this? Let me also help you out with something else. Let's see. We know that sometimes it's when you want to take the inverse Laplace transform. Let's see, of this here. Let's see. If I take the inverse Laplace transform of this is not in my notes, but it's actually in my solutions to the Weber-Sign problems. Just want to show you another way it could help you out on the exam. I want to take the inverse Laplace transform of this. We know that this is let's see. Yeah, we know that this is t to the n, right? But sometimes it's easier to deal with the inverse Laplace transform of 1 over s, because this turns up quite a bit to some power of n. Sometimes it's easier to deal with this. Okay, so yeah, so many times you will see in solutions to differential equations something that looks like this, and you could use this to come up with this. Okay, but it's actually easier. Let me show you how I can come up with this. Right now we don't know what this is, right? But I could factor out the n factorial. They can factor out the n factorial and write it like this. Okay, so yeah, let me do it this way. I'll factor out the n factorial. So I got the n factorial out. And then I say, okay, let n become n minus 1. Okay. So when I do that, let's see, this is still t to the n. Okay. So when I do that, if I let n equal to n minus 1, then this is going to become n minus 1, the inverse Laplace transform of 1 over s, right? And then this is going to be t to the n minus 1. So in other words, I could say that the inverse Laplace transform, or this would be n, the inverse Laplace transform of 1 over s to the n, I can also write it as, this is factorial. I can also write this as a t to the n minus 1 over n minus 1 factorial. Now, did I do that too fast? This could actually help you on the exam. That's why I'm showing you this. It's another way of doing it. It's another way of looking at it. Let's see. Okay. So once again, the inverse Laplace transform is this, right? But as all I'm doing here now is I'm taking this here and I'm factoring out the n factorial, and then I'm replacing n with n minus 1. So now this is, let me make this clear. This is n minus 1 factorial. Right? This is n minus 1 factorial, right? And then I could, okay, and then I just bring the n minus 1 factorial down. So if I ever see any power of s to the n, I could just, and I want to find the inverse Laplace transform of 1 over s to the n, it would just be written like, to write it like this. This is sometimes easier to use than this. Okay. Now, let me, now here's a, let's see if you can do this. What if I gave you now, if I said to you, I want you to try to figure this out. The inverse Laplace transform of 1 over s minus 7 squared. Try to do that. What is this equal to? The inverse Laplace transform of s minus 7 squared. Give you a couple of minutes. It shouldn't be hard. Okay, I'm going to do it now. Hopefully, the easiest way I think to do this is first consider this. First consider the inverse. Make sure first consider the inverse of 1 over s squared, right? And what is that going to be equal to? Well, I can use the formula I just gave you here now. I could use this or this, but I find this one easier to use. So this is just going to be t, right? This is just going to be t, and then divided by 1 factorial. So this is just t, right? So the Laplace transform of this is just t. But now I have this property here, right? I got this property here. So the Laplace transform of this thing, I'm going to get rid of them. Laplace transform of this thing is going to be t, right? It's going to be t because I got the s squared, but now I got the shift, okay? I got this shift. So this is going to be e, and it's going to be 7t, right? So the Laplace transform, the inverse Laplace transform of this thing is t e to the 7t. I like to write, yeah, that's a good way to write it. I actually like to write the exponential after if this is the polynomial. All right. So you see this here is just t, but now I'm applying the rule here that whatever value my s's, I have to shift my s's, right? I got to shift my s's. And here I have to shift it 7. I got to shift the 7, so that's going to make this an e to the 7t. Does everyone understand this? You do have to use this, and this is very the problem that you have to solve on the exam. You're going to need to use this, and it's not, it's with different numbers, but the same exact idea. Okay. Let's do a couple of more problems. I'm not going to do anything new. Okay. I covered everything that that we need. I covered what you need for the exam. Wonder if I should start new stuff. Okay, let's see. Okay. Let's see if you could try to do. I want to give you a chance. Now, on this next exam, you don't have anything as hard as this, but if you could do this, you'll definitely be able to do what's on the exam. Okay. I want you to find the inverse Laplace transform of this. Okay. Let me give you some time to work it. Don't look at my notes. Partial fractions. Okay, so everybody's trying to solve the inverse Laplace transform of this. The inverse Laplace transform is always harder than the Laplace transforms. Just like integrals are always harder than derivatives. And let's see. Back in a second here. Break this up into partial fractions. Okay. All right, let me go ahead and solve this one, and then I'll give you another one to solve. So what I'm going to do is I'm going to break this up. I'm going to write this as I'm going to write this as 2s. Remember partial fractions that, well, I need to write that again. So I'm going to break this up into a over s minus 3 plus b over as minus 3 squared. Remember, we have if you have the denominator here, you have to break it up like this with this form. All right. So this is going to give me 2s plus 5 is going to be equal to a times this is going to be s minus 3, right? Plus b, right? When I multiply both sides of the equation by this, right? Like this cancels with this. Okay, everybody knows how to do this. All right, so let's see. So what do I got now? I get 2s plus 5 is equal to as minus 3a plus b. Okay, so when I compare, here I got an s, here I got a 2 times an s, here I got an a times an s. So this is telling me that a is equal to 2, right? A is equal to 2. Then here I got 5 is equal to 3a plus b, or this is minus, right? Like 5 has to be equal to 3a plus b. So let's see, and a is equal to 2. So this is 5 is equal to minus 6 plus b, right? So this is telling me that 11 is equal to b. Okay, so now what do I have here? I have that, let's see, I have, this becomes, so now I have the inverse Laplace transform of 2, right? 2s minus 3 plus, let's see, this is 11. And then this is s minus 3 squared. Okay. All right. This is, okay, so now, you know, this is, I might have left this step out in my notes. Right? I'm just using the linear property of Laplace transform, but you could just jump right to the next step if you want. Okay, so what is this? This is just 2, right? I can factor this 2 out. This is 2, and then this is 3t, right? Remember, you have to remember that Laplace. See, the other thing too, if you understand the basic Laplace transform, you know what you need to get to. Okay, so hope everybody sees this is one of our, I guess you know, one of our Laplace transforms. It's very important to know is that s minus a, right? This is equal to e to the at, right? So I'm using this property that we did yesterday, right? We did this property yesterday. So I get this. Now this one here, okay, I hope everybody sees that this is going to be 11. Now this here is going to be a t, right? This is t, but it's shifted by 2. So in other words, this is a, yeah. This is a 3 here. Sorry, that's a 3. Okay. I thought I screwed something up for a second. So that's a 3. I copied a 2. All right. So this is going to be let's see. Well, let me. Right. This is, I got 11 over s squared. Right. 11 over s squared. Now the s squared, if I didn't have the minus 3 here, right, this would just be 2. This would just be t. Right. In other words, the inverse Laplace transform of this would be 11t. Right. but I got this shift of 3 here. So this is going to be 11t times e to the 3t. All right. You do need this property here for the next exam. Okay. Does everybody see that what's happening here? Right. This is the 11 over s squared, and that's just 11t. If I just had this, right? If I just had this, it's 11t. But I got the -3 in here, right? I got this -3 in here squared. So because of that, this becomes e to 3t, right? Because we're using, where's the inverse? Let me get my notes here. Okay, so we're using this inverse property, right? We're using the inverse property here. Okay, let's do one more problem, and then I think I'm going to let you download the exam. Unless you have questions, I'll be happy to answer any questions, but I want to do one more problem. We'll have you try to do one more problem. Let's see. Okay, so let's see. So try to do this problem here, Lou. Now, when you see something like this, when you see a square and you get, you want to complete the square. Okay, so let's see. So try to find the inverse Laplace transform of this. To solve this problem, you're going to need this as well as the shift. So I wrote it down. All right, let me go ahead and solve this. First, what I'm going to do when you see something like this, where you have, a first order S, second order, and then you want to complete the square. Okay. So, so how do we complete the square, right? I can write this as, remember, to complete the square, you all know from pre-calculus how to complete the square, or from high school. I take half of this and square it, right? So I'm going to, half of this and square, I'm going to add a 16. Then I have to subtract the 16, right? I can't just add a 16, I have to subtract the 16. Okay, so now this is a perfect square, right? And so what I got here, on this here, I just got 4, right? 20 minus 16 is 4. Now this here is a perfect square. This is going to be S plus 4 squared, all right? So what I got here now, in the bottom, I rewrote this to make this a perfect square, right? So I got S plus 4, right, squared plus 4. So now I want the inverse Laplace transform of 1 over S plus 4 squared plus 4, right, plus 4. All right. I think, so you see it. What is the, if I just had this, the inverse Laplace transform of 1 over S squared plus 4, right? Forget about this 4 here, but what if I had the Laplace transform of this? Well, this would be the sine, right? This, using this prop, this would be the sine of 2t, right? But I need a 2 up here, right? Because I need a 2 up here because I got this k squared, so this is 4. I need the 2 up here, so I got to put another 1/2 down here. So I hope that everybody sees that if I had this, right? If I had, I'm just forgetting about this 4 for a moment. Okay, I'm forgetting about this plus 4. So that tells me that the inverse Laplace transform of this is just 1/2 the sine of 2t. But now this, I got the shift of plus 4, right? I got the shift of plus 4. So the Laplace transform of this thing is going to be 1/2. In other words, I can put the 2 here, put the 1/2 here, right? And so this is going to be, it's going to be E, it's going to be, I can write it as 1/2 e to the minus 4t, right? Minus 4t times the sine of 2t, right? So finally, so the inverse Laplace transform of this thing, okay, is, well, let me just write it down here. So the inverse Laplace transform of this thing here is equal to, I didn't leave myself enough room, 1/2 e to the minus 4t, and then times the sine of, and then in here is the sine of 2t, right? So that's the inverse Laplace transform. I couldn't fit it in, the sine of 2t. All right, are you getting this? Any questions? I found in the past that sometimes students have problems with the shift, but it's really pretty straightforward once you do need to practice some of these. Okay, and you see here, like I said, I want to do a couple of problems with a shift because the solution to, I gave you a first order and a second order, and actually the first order is a little bit harder because the first order problem you have to use the shift, the second order problem you don't. Okay. The plan for now and the rest of the semester is that, the next 2 days we'll continue with Laplace transform and finish up Laplace transforms. And we'll be going into the real advantage of Laplace transforms is when we could solve, equations where we have maybe a pulse, okay? We have piecewise continuous functions. And that's the real advantage of Laplace transforms. Like I said, they become important in electrical engineering and control theory. Okay, let's see. Okay, so as I was saying, the plan between now and the end of the semester is that we'll finish up Laplace transforms today, yeah, Wednesday and Thursday. We'll be able to finish up Laplace transforms Wednesday and Thursday. Okay, and then on Monday and Tuesday, we'll do systems differential equations, and we're only going to have. It's only required that we do like one type. We're going to do system. We're going to do just a linear system of differential equations under certain conditions, and that's the only thing we're required to do. So we'll do that next Monday and Tuesday. So then Tuesday we'll have the fourth exam, okay, and then on Thursday we have the final. Okay, so next Tuesday will be the fourth exam. I haven't made up the fourth exam yet, but it will be Laplace transforms. The fourth exam will be Laplace transforms and also a system of linear equations. And it'll probably just be one problem on the systems of linear equations. So we're going to do a little bit of the linear algebra next week. Next week we'll do a little bit of linear algebra, because that's how we're going to solve a system of linear equations. We're going to learn about eigenvectors and eigenvalues. How many students have taken a class in linear algebra?
During the first summer session.
Oh, you're taking it right now for summer session?
No, I took it in the first summer session.
Oh, you took the first summer session. Okay. All right. Well, what we're going to do I'm going to show you how to take the eigenvectors and eigenvalues of a matrix. And that's how we're going to solve systems of linear equations. It's pretty straightforward. Like I said, the problems that we're going to do, it's just going to be two systems. It's just going to be a system of two equations. Okay.
I have a question.
So yes, go ahead.
What's the final answer for this problem?
The problem we just did?
Yeah, the one that's on the screen right now.
Yeah, it's 1/2. Let me write it. Need e to the minus 4t sine of 2t. Right? That's the final answer to this. Okay.
Okay, thank you.
Okay. All right, what I'm going to do now, I covered what I wanted to cover. I don't think we have any problem. We still have 4 more classes, and I'll be able to cover everything I want to cover in the next 4 classes. We don't do a lot with systems of equations, but it's actually pretty cool what we do. And it's easy to, once I show you the basis of what we're going to do, if you have more complicated problems, it's just dealing with more complicated matrices. All right, so what I want to do now is you'll be able to download the exam. I'm going to turn that on. So make sure before you leave, you can download the exam. So I'm not doing anything, the day you have the exam, I normally not have a full class. So let's see. Not keep